Well, great. Well, then we will kick you in to the content. So Wendy Kuhn is going to speak to us about using serverless frameworks to do webhooks in a scalable manner. And then you have to shake your fist when you say that. And then the second thing we're going to do is an open discussion on the current state of configuration management, which I'll moderate and use the whiteboard, and we'll all talk about what's going on there. So with that, I hand it off to Wendy. You can use the stick mic there. You can wander around with this one based on what you want to do.
Okay.
I don't know, say something.
Is that a good volume? Too loud?
No.
Just right? Okay. All right. Well, thank you for coming. My name's Wendy, and I'm going to be talking with y'all tonight about Nami, a serverless framework for consuming webhooks at scale. And I did work on this project with a team of 2 other devs. It was built using Node.js and the AWS SDK for JavaScript. Nami is a command line interface tool that deploys a primarily serverless architecture of AWS services for handling bursty webhook traffic. It is published as an NPM package, and it is open source. So here's a little taste of the deployment sequence. So you can see each piece being deployed, and then we output the endpoint that can be registered, subscribed to a webhook. So any AWS users here?
All of them.
Yeah, okay. So I'm sure that y'all are familiar with the learning curve and some of the hidden complexities that there can be when you're deploying services on AWS. So even a task that seems seemingly simple and discrete can actually be comprised of multiple microtasks under the hood. And then when you're trying to get these services to talk to each other, obviously that complexity grows. So that's the complexity that Nami abstracts away from the developer. All right, so I'm just going to do a brief review of webhooks and event-driven architecture. I'm going to talk about Nami and the problems that it solves, and then some of the design decisions that we made while building it, some challenges that we encountered along the way, and some optimizations that we were able to make in response to those. Any webhook users publishing or consuming? Great, awesome. All right, so webhooks are user-defined HTTP callbacks. So let's talk through an example of a general webhook cycle. So say we have an online store that integrates with Stripe for its payment processing. So when a customer makes a purchase, then that's going to create a credit card transaction event to occur on Stripe. In response to that event, Stripe will then make a post request to the URL endpoint that the store has subscribed for that event. And then in the body of that request, that's going to contain all of the event information related to the event. Oops. So webhook payloads are typically JSON, but they can be other formats like XML or form data. In this example, it's JSON. So when the endpoint actually receives the request, it can just send back a status 200 successfully received. And now the store has all of the relevant information that they need to do something. And in this example, that something is to initiate a workflow to get that product sold and ready to be shipped. And so here's an example of actually subscribing to a webhook, and this is with GitHub. So you can see the Nami-generated URL endpoint. That's the payload URL field. And then GitHub does allow you to select content type, so JSON in this example. And then you'd go on to select the event or events that you would like to trigger a request to this endpoint. So it's the body of the request that will contain that JSON object with the event data. So here's an example of event data, not from GitHub. This actually represents a payload from Shopify representing that an inventory item has been created. So all the properties in the object are details related to this event, including the time at which it occurred. And this is actually the only thing that the webhook producer and consumer have to agree on, is the structure of the event object. So the webhook producer publishes the expected structure, and then the consumer can implement logic to handle it based on that structure. So webhooks are really just about moving data from point A to point B. Sounds a lot like APIs, very similar, but one big difference is who's driving. So APIs were really seated in a request-driven paradigm where a client has to initiate a request for data to the server, and then the server responds synchronously. But since the client can't predict when an event is going to occur on the server, they have to send these requests at regular intervals, just hoping that there's going to be some data sent back. But it's only after an event occurs that the server has something useful to send back, right? So you can see just by looking at this, it's a pretty inefficient way to transmit data. It does create an unnecessary load on both systems. So the client, because it has to send all of these requests, most of which are going to be unfruitful, and then the server for having to respond to all of those requests. And that problem becomes especially pronounced when data is only sometimes or rarely available. But webhooks turn the situation around into a don't call us, we'll call you scenario. So a request is only fired off from the producer when the event occurs. So you can see, just by looking at this, compared to the last slide, much more efficient way to transmit data. And with webhooks, the producer doesn't actually need a response from the consumer to continue with some task. So with APIs, in this request-driven paradigm, we're synchronous, so the client does need to wait for the server to validate and process that request before continuing execution that depends on that information. It's also request-driven, so the client does have to initiate the request, and here the response is meaningful, so the response from the server does include information that the client needs. But with webhooks, we're moving away from this synchronous and request-driven paradigm and really toward an event-driven one, which is just responding to events as they happen. So you can see that the terms client and server are no longer relevant here. We're really just talking about event producer and event consumer. So with this event-driven architecture model, we're working asynchronously. So the producer doesn't have to wait for the data to be processed. It just announces events after they've happened. And it's also event-driven. So the event data is actually just being pushed after it occurs. And so there's no more polling occurring here. Also, the response here is really just acknowledgement only. It's not meaningful. The event's already happened. It doesn't need to be validated. The fact that the response is even happening here is just because with webhooks, we're working within the limitations of the HTTP protocol, so a response is required. And the decoupling that we get here with an event-driven architecture allows producer and consumer to receive and process events at different times. It allows them to be scaled separately and to be implemented with different technologies. So that's all great, but that asynchronicity and event-driven updating do come at a cost. And that's that we can no longer control the flow of data because events just happen when they happen. So when batches of events generate many webhook requests instantly, that kind of traffic pattern does threaten to overwhelm the consumer with a massive wave of webhook data. So some examples. So the engineering teams at Jira and Rewind wrote about experiencing exactly this type of problem. So first, Jira, project management, issue tracking software. So the internal service that they use to automate this issue tracking does so using webhooks. And anytime an issue is added or deleted or modified, that's going to generate a webhook. And so when users were updating or adding or deleting issues in bulk, then that was generating a webhook request for every single one of those issues. Another example, so Rewind is a company that uses webhooks to make real-time backups of Shopify users' store data. So you can think of this as something similar to Apple's Time Machine, but for Shopify. So they were seeing this kind of traffic pattern when Shopify customers were doing things such as importing entirely new inventories. So for example, they import an inventory of 10,000 items, and for each and every one of those items, there's going to be an inventory item created event that triggers a webhook request. So they were being hit with a massive wave when customers were sort of doing batch operations like this. So that's our first problem, bursty, inconsistent webhook traffic. So with our event-driven way of transmitting data, you can't control the flow. So the consumer can't just tell the producer to slow down when it's being overwhelmed. So what does this kind of traffic pattern look like with always-on servers? So here, your system's happily handling incoming requests until you're hit with that huge wave of webhook requests, but no means to scale your servers instantly, so the infrastructure just can't handle the load, and then you drop data. So what's the off-the-shelf solution to that? More servers. So purchase hardware, extend your backend code, deploy the additional infrastructure, and you're good to go, assuming that you've predicted the worst case scenario. But problem here is between the squiggly line and the dotted line, and that's all idling resources, right? So that's expensive. So the question here is then, can we dynamically adjust resources based on demand? And yeah, we can do that with Lambda, so AWS function as a service offering. Other vendors, of course, include Google Cloud, Microsoft Azure, and others. So with function as a service, so with FOSS, your code is being run in ephemeral compute containers, and there's no servers to provision or manage. That's all handled by the platform. So you're just uploading your code, and all scaling is completely automatic and elastic. So there's nothing to configure on your part. So you're only paying for time spent executing and not idling. So Lambda functions, great helpers, because they show up when they're needed, as many as you need. They do the work you need them to do, leave as soon as they're done. So you're only paying them for the precise amount of time that they spend working. So zooming out for just a second, let's look at serverless. So obviously the name itself is a misnomer. There are actually servers running your code, but the management of the servers and the processes is all abstracted away. So it gets the name serverless. So here we're looking at a continuum of infrastructure management. And to one extreme, there's bare metal, physical on-premise servers, of course. And then you hop onto the continuum, and you've got infrastructure as a service. So the machines have been virtualized, but you still have to manage operating system, networking, security, etc. Then on the other end of the spectrum, this is where we have serverless, FOSS, and BOSS, so backend as a service. So with FOSS, all of the provisioning and management, as well as all of the scaling, is completely handled for you. So it's really that automatic scaling that we're leveraging to handle the burstiness of webhook traffic. The trade-off that you have here with that great ease of use is less control, though. For example, you don't have any control over or introspection into the life cycle of a compute container. So, here's a Lambda compute container. So when a Lambda function is invoked for the first time, a container is spun up and it's provisioned with all of the resources, the memory, the dependencies that are needed to execute your function. So multiple functions can be executed sequentially in the same container. So as long as that container isn't currently in the middle of executing another function, then when another invocation is triggered, it can be reused. And as long as the container has been used relatively recently, then it stays warm for more function executions. So no scaling happening here. So let's look at Lambda scaling. So for our use case, for a large number of events being generated over a short period of time, so that bursty traffic, then that's going to mean that the rate of incoming requests is going to be greater than the time it takes for a container to complete processing the current request. In that case, another container is going to have to be spun up when that second request comes in. And then the third request comes in, those two containers are still busy, so another container is spun up, and so on and so on. So it's these multiple containers that are really what enable Lambda concurrent executions. So that's the unit of scale for Lambda, concurrent execution. Although we can't scale to infinity, AWS does impose a default per account limit of 1,000 concurrent executions. So now, this is what Lambda scaling looks like with our bursty traffic pattern. So each circle represents a container, and they increase concurrency with more requests, and then decrease concurrency with fewer requests. Perfect. So Lambda's totally taking care of our bursty traffic pattern, but the data still needs to be throttled and processed, and then put to rest for later retrieval. So let's look at a system that can take this event data on its journey from the request being received to being put into a data store. So Nami's solution stands up this sort of constellation of AWS services. So we have API gateway, a Lambda layer, an SQSQ, another Lambda layer, and then our data store on an EC2 instance. So this is the path that the event data will travel. So what does it take to stand this up? There's a few ways. So you could do this via the AWS Web Console. That is a lot of clicks. And then if you want to handle another subscription, you've got to do that all over again. You could do this programmatically via the SDK. And that's exactly what we did. And counting the API calls, it does take over 50 to stand this up. And with either approach, you have a complex process. So there's a considerable amount of knowledge that's needed about each service. and it can require some digging and a little trial and error to determine the right sequence of commands. So this is all time spent away from your core business problem. So we really needed to abstract this complexity away into a framework. So that's what we did with Nami. So we bundle all of that functionality that's needed to stand that up into a single command. So now I can walk you through some of the design choices that we made during development. And so here's just a breakdown of the components. So not many, but there's a lot happening between them. So let's look at each one. So Lambda, this is the core piece of our architecture. It's receiving the request, it's handling it by sending it on to be stored, and then it's returning a response to the producer. So with this Lambda, we really needed to keep the execution logic lean so that we can provide a quick response to the webhook producer, and because we want to maximize scalability by minimizing function execution duration. So all this function needs to do is send the payload on to be stored and then return 200 status. So now we need to actually store the data so that the developer can hook into it for further processing. And we do that with MongoDB deployed with Docker on an EC2 instance. So we have chosen MongoDB, NoSQL database, because a document database is a great fit for the nested JSON structure of our webhook payloads. And since our framework is meant to handle webhooks coming from any producer and for any event, we expect the schema to be volatile, so we really do need that schema flexibility that a document database offers. So AWS does have some managed service offerings for database, but we don't use one for a few reasons. One is that our use case doesn't really call for any of the features of a managed service. Also, some of the offerings that could otherwise be a good fit actually cost more for write-heavy usage, and we are write-heavy, so definitely not what we want. Also, they're less mature as services than MongoDB, which has been around over a decade. So in the absence of a really compelling reason to use one of those managed services, we do prefer to return control back to the developer when the data's at rest. So we do deploy MongoDB on an EC2 instance, of course, AWS virtual machine offering. And we do this automatically by passing in a bash script to the SDK call that's used to run the instance. We did choose to deploy the database with Docker as opposed to direct installation because the containerization that we get with Docker decouples the application running inside of it from any host system configuration. So that way we avoid potential for conflict between the install and the host system. One caveat about EC2 instances is that they only have ephemeral instance storage by default. So if the instance were to ever temporarily stop and restart, then any data in memory would be lost. So we overcome this by attaching an elastic block store volume to the instance. So EBS, of course, AWS disk storage offering for EC2. So in this code snippet on the third line, you can see where we do the volume mapping of the EBS volume to the MongoDB data directory. But there's a few significant problems introduced here. So with many thousands of requests coming in at any given second, we do run the risk of overwhelming the number of available connections that the data store EC2 instance can handle. So we need to slow down the flow of data so that we're not overwhelming our downstream resource. And while it is possible to provision a larger instance size that can accommodate more incoming connections, we'd still be left with this problem of tight coupling. And with tight coupling, we do have a potential for data loss with any downtime of the EC2 instance. So we need to introduce some fault tolerance to our system. Also, we really do want to work with the event-driven model rather than against it. So if we hold the connection open to the webhook producer while we open a connection to the database, process the payload, write the document to the database, and then finally respond to the producer, then we're really undermining that concept of the asynchronous consumer, which is one of the major benefits of an event-driven architecture in the first place. So if we do that synchronous processing, then the producer becomes subject to the consumer's processing time and failures. So what we really need is for the Lambda to just fire and forget the webhook payload. So it can send it on to be stored without waiting for that process to complete, and then it can immediately return a response to the producer. So this is what we should do. Get it, store it, act it. So don't do processing while holding that connection open. Lambda just fires off the webhook data without worrying about how it gets stored. You can just trust that it will be. So to address these issues, we do insert a queue between the Lambda layer and the data store. And the queue acts as a message broker for us. So it queues, routes, and delivers messages. And it's optimized for high concurrency and throughput, so it scales well. And the queue is doing several things here in our architecture. It's throttling message velocity, so it slows the flow of data by buffering those messages until the consumer is able to receive them. It also introduces some fault tolerance in case of failure. And it does enable asynchronous processing by decoupling event producer and event consumer. So with this decoupling, we're really fully embracing the asynchronous and event-driven nature that a webhook handling system should have. So the producer doesn't need to know anything about what the consumer is going to do with the message, or even if it's available. And the consumer doesn't need to know anything about the producer. It can just count on messages coming out of the queue. So producer and consumer can scale separately when decoupled. So our producer, the Lambda that we were just talking about, that can scale way up, can scale without overwhelming our consumer. Okay, so the queue is an integral part of our system now, but the trade-off with this additional infrastructure complexity introduces a few new questions for us. And that's, how do we get messages from the queue to the data store? How do we perform any necessary processing on the payload before we actually store it? And how can we allow users to send that data to other external systems? So the answer to that is another Lambda layer that acts as the message consumer. So this Lambda can open a connection to MongoDB. It can perform any processing on the payload before we store it, and allows users to send data to external systems. But now we've introduced another problem. So recall when we were talking about Lambda's awesome auto-scaling capability. Well, in this case, we actually don't want that because then we're just reintroducing the problem of overwhelming downstream resources, and we're competing for concurrency with the Lambda that receives the webhooks. So to prevent this unwanted auto-scaling, we do set the maximum concurrency on this Lambda to 5. So that gives it just enough concurrency to receive and process those messages at a throttled rate. And we do want to be really intentional with our error handling in the message consumer. So in the event of an unprocessable message, a poison message, or a message of death, as they're sometimes called, then in the event of extended downtime of the EC2 instance, then the message just won't be able to be delivered. But we don't want to rely on the default retry behavior of SQS because it'll just continue to retry sending the message indefinitely until the message retention period expires. And we don't want that for a couple reasons, because AWS bills for each send with SQS, and the data is ultimately going to be lost at the expiration of the message retention period. So instead, we configure a dead letter queue, and that's a place for those unprocessable messages to come to rest for later analysis and processing. So now we have our webhook receiving Lambda, receiving messages from the queue, and then storing those payloads in the database at a pace that we can keep up with. But how do we ensure that that data is not accessible by public internet? And the answer to that is virtual private cloud. So we can securely isolate those services inside of it. The EC2 instance is required by default to be in a VPC, and so we just make the webhook processing Lambda part of the same VPC, and then it's able to write to the database but without opening up a public portal. And finally, we do create an entry point to our infrastructure where the request actually comes in. So that's the API gateway. So those webhook requests do need to be sent to a publicly available URL endpoint. Lambda alone doesn't provide this, so Nami uses API gateway to publish that URL endpoint that can then be subscribed for webhook. The endpoint is configured to invoke the receiving Lambda when it's visited, and then the gateway routes the Lambda's response back to the producer. If a user does deploy multiple instances of Nami, then we do consolidate all of those endpoints under one host using different paths. And we do that instead of creating a new gateway for every instance, so we don't strain the overall per account limit imposed by AWS for a number of gateways. Okay, so remember when I said over 50 API calls, not including helper functions or scripting or anything else. Okay, so now that we've walked through those pieces, hopefully you can get a sense of how big of a task that is to do manually. So that's where Nami comes in. You can deploy with one command and then grab that endpoint and go subscribe it. All right, so during development, we did encounter several challenges along the way. But we were able to build in some optimizations in response to those. So I'll walk through those. So one of the optimizations that we did make was to have the webhook processing Lambda to reuse existing database connections. So a Lambda container has a shared execution context that's accessible by any function that's run in that container. So we declare a variable in that context and assign it to the database connection. So when functions are invoked, if the connection exists, then it's used, and otherwise it's created, and then it's available for use by all future invocations in that container. So we do reuse the existing database connections, both to reduce overall execution time and just to better manage open connections. So Lambda memory optimization. So during development, we did notice some throttling occurring on the webhook receiving Lambda. And we know that increasing memory size of a Lambda compute container typically decreases function execution duration. So we increased the memory size from a default of 128 megabytes to 256 megabytes. And that did give us the best response times for our use case, and that took care of the throttling issue. Another question we faced with running Docker on EC2 was, what happens if an EC2 instance were to temporarily stop running? So Docker containers need to be run in order to be used, but they do stop running when their host system stops running. So to ensure that the container will always be available and running as long as the EC2 instance is on, we just configure this automatic restart policy. Finally, we did encounter some challenges with timing when deploying or destroying services in rapid succession if those services depended upon one another. And that's because AWS returns an optimistic response when an SDK function is invoked. So it can sometimes happen that the service is not actually in the expected state when you need it to be immediately after that successful response. So to overcome that, we did implement some basic looping to continually check the status code of the services until it was in the appropriate state. So here, this is just illustrating after running the destroy command with the termination of an EC2 instance, we really needed to ensure that it was completely stopped before we were able to delete the associated security group without error. Some future work for Nami. So we've considered adding monitoring alerts that would let the user know if a message has entered the dead letter queue after failing to be written to the database, or if the main queue is filling up too fast so that they could then manually intervene, perhaps increasing the concurrency limit on the processing lambda. Also, customizability. So it's definitely possible for the user to go change and customize any of the resources deployed via Nami with the web console. But we would like to add support for users to be able to customize those details at the time of deployment by passing in a flag. So some of those things that users might want to customize: the EC2 instance type, the persistent storage volume size, memory and timeout limits for Lambda, custom error handling and response codes, or a custom message retention period, either for the main queue or for the dead letter queue. And that's it. Hope that wasn't too long. If you want to learn more about Nami, you can read our case study there, and you can get in touch with me this way. And thank you for listening.
Take any questions?
Yeah, absolutely.
I've got one. So do you have any stats on kind of cost per, cost per 1,000 requests of this setup?
So you mean the costs that are published by AWS? Or,
yes.
Okay. Yeah. Yes. Not on the top of my head, but is there a specific one? I might be.
Well, no, just wondering, if you're using this and putting scale through it, the SQS charges and the Lambda's
Right.
charge. I'm wondering just what somebody could expect if they're like, okay, I'm gonna use this and put, put
Yes.
1,000 requests a minute through it for the whole month. What's that gonna look like?
Yeah, absolutely. Yeah, AWS does make that information readily available. I don't have those numbers memorized, but that would certainly play into some of the customization that a user might want to do, just depending on their use case and specific traffic pattern. But yeah, so I will say that so Jira and Rewind, those engineering teams actually did write about the cost savings benefits that they had after deploying serverless architecture with AWS. It's a little bit different from Nami, but certainly, definitely something to consider is that cost saving.
Kind of related to that, using kind of your default setup there, what's the maximum sustained number of webhooks per unit time that it'll do?
So for our system, we did do some load testing, and so we were aiming to support around 5,000 requests per second, and we did get up to, let's see, about 4,000 requests per second with 0 errors, and up to 4,800 with maybe 3 errors, I think it was. So that's, with these configurations, that's about what Nami supports right now. Oh. You, Kane.
I'm not familiar with Nami, and my browser spam illness all over the place. How do I look that up on find out more information?
About Nami? So you can read more about it at this address, and then that will also link you to the GitHub if you are interested in going there. I'm not sure if that's readable from there, but I can definitely write it down for you after if it's, yeah.
You can also just post it to the meetup comment page.
Okay,
That would
great,
be
yeah.
sweet, yeah.
Post in the meetup comment.
Did you look into RabbitMQ or Kafka perchance to as a solution there besides SQS or
Yeah.
was it more expensive or?
So we did consider Kafka, and I think for the cost-benefit analysis that we did, so it's definitely a bit trickier to configure there in the middle of our architecture, and we just didn't. So with the use case and the load that we were aiming for, we didn't need the capacity that Kafka has, and also we only have a single consumer, so we did decide to use SQS because it can be configured as an event source trigger for Lambda, and for this use case, simpler to configure, so we did stick with SQS.
You mentioned monitoring. Do you consider any specific tool?
For monitoring?
Yes.
So I think what we would do if we were going to add monitoring is, so AWS has a very robust CloudWatch monitoring suite. So what we would probably do is just allow either custom or we would just configure those alerts on those specific events within the deployment of the framework.
I have a comment on your slide talking about going from EC2 to serverless, and you say you have more control versus, but the other thing is as you get away from the VM, you also get locked into a particular vendor,
Mm-hmm.
right? Because like on the EC2 stuff, you've got something that's going to configure a provision, right? But as you get into Lambda or whatever platform, now you have to rewrite everything if you want to move.
Yeah. Excellent point. Excellent point to consider.
Did you consider, so it sounds like you kind of hand orchestrated the provisioning of the different pieces. Did you consider using CloudFormation and having kind of a template to do the provisioning, that you wouldn't have to kind of worry about the waiting for each individual thing and all that, and it could do that orchestration for you?
Yeah, so certainly an option, but CloudFormation is proprietary, and we did want to approach this from a problem-solving standpoint. So if we, in the future wanted to migrate to other platforms, Google or Microsoft, it's a possibility.
I was going to ask a similar question about your choice for NPM as the packaging tool.
Mm-hmm.
You thought, first thought, CloudFormation, I was thinking like Terraform, Lambda, or something like that. Seems like those have a lot of the API interfaces for you, there's subscriptions. Does NPM offer something that those platforms wouldn't
doesn't answer your question, but we did choose Node to build Nami because Node being asynchronous and non-blocking by nature seemed to be a good fit for this really event-driven pattern that we're handling. So with webhooks being event-driven architecture, and the asynchronicity that Node provides us, that's
So is Nami end up running as a service as part of this infrastructure, or is Nami basically the packaging that allows you to build the infrastructure?
that's right. Nami is just the tool that deploys the infrastructure.
So question on the consumer side of things, like once you have, let's say you're doing the post process work from your application point of view, would you go pull the data from MongoDB or whatever, and start working on it from that perspective?
Yes, I think I heard your question. So, yeah, at the point that the data is at rest in the MongoDB store, then yes, you can retrieve it from the data store there and begin processing. Or, optionally, you could actually lock that off and just go ahead and send that data on to another external system. I mean, it's customizable, so.
Okay, so like the Nami consumer can just say, hey, go ship this data off to this whatever other database.
Yeah,
Okay.
yeah, absolutely.
And I guess you can make the decision that second row of lambdas, you can put more or less business functionality into it, right?
Yeah, absolutely. Yeah, that's totally customizable. We do actually also have, so you can just go ahead and deploy the infrastructure with the deploy command and that's it. But you can also, before deploying, you can run the create command, and that actually drops the directories, the files that you need locally, so that you can go ahead and modify those before even deploying. And we actually do recommend that that users, for example, add some authentication logic in the webhook receiving lambda. So you certainly want to make sure that you're receiving those requests from the source that you expect.
That was totally my next question, as to where the preferred place to put that.
Okay,
is
yeah.
in this, so the actual receivers.
So
you
for
don't have to pay for garbage going through your SQS queue.
So for validating the source of the request, definitely the receiving lambda. But if you want to do any more heavy lifting processing, that really needs to be on the other end, because you really want that first lambda to have that really lean logic so that you can just immediately return a response.